All right, we're going to look right now at basic rational functions. Now, basic rational functions are functions with the form y equals a over x, like that. Now, before we actually look specifically at basic rational functions, we're going to talk just in general about what is a rational function. And then we'll move on to thinking about patterns and tables of values for basic rational functions, and then what features you can see in the graph, and a quick way to generate values for tables and graphs for these basic rational functions. So let's turn now to look at what exactly is a rational function. A rational function is one that can be written as the ratio of two polynomial functions. So it can be as simple as something like y equals 10 over x, or it can be the ratio of two linear functions like that, or it can be the ratio of two quadratic functions or higher, or any kind of combination of any of those things. In general, it's an algebraic fraction, a way of thinking about it, right? Where you have polynomials on the top and the bottom. You can have one of the polynomials can be a constant term like that, or they both can involve variables. That's what a rational function is. So let's now turn to some that look more or less like this first one, a basic rational function where you have constant divided by x. Now, to start with here, we're going to look at just about the simplest rational function you could come up with, and that's y equals 1 over x. We're going to put in some x values here, and we're going to see what y values we get as a result. It's going to fill them in automatically, but then we're going to think about the pattern that we see. So to start with here, I'm going to put probably the simplest one I could think of as an x value is 1, and see what we get there. We get 1, of course, because 1 divided by 1 gives us 1. Now we're going to do two things from 1 here. We're going to make the numbers larger and larger from 1. Now we're going to go kind of 10 times as much at a time, just so we can quickly see a pattern here. If we put 10 and 100 and 1,000 and then say 10,000, and then that's probably enough to see what our pattern is. And then we're going to do from the other side of 1 here, we're not going to make it larger and larger. We're going to make it smaller and smaller, but we're going to head towards 0. We're going to continue our pattern here, and we're going to go 0.1, 0.1, 0.001, and say 0.0001. All right. So we've gone two directions from 1 here. We've gone bigger and bigger numbers, and we've gone smaller and smaller numbers, heading away from 0 and heading towards 0. Now look at what the y values do here. As you increase x, make it larger and larger, the values of y get smaller and smaller. They approach 0. And as you allow the x values to get smaller and smaller, in other words, as you let the x values approach 0, the y values get larger and larger. The y values head towards infinity as the x values head towards 0. And then vice versa over here. As the x values head towards infinity, the y values head towards 0. Now, we're going to look at that pattern on the other side here of 0, because we could have just as easily put in -1. And now we're going to do the same thing with that. We're going to head away from 0 and towards 0 with negative values. So I'm going to really quickly fill those in here. On the negative side here, we get exactly the same pattern, only with negatives, because, of course, when you divide 1 divided by a negative number, you get a negative result. Now, we're going two directions here from -1. As you allow the x values to head towards negative infinity, as you make them more and more negative, the y values head towards 0. It might not seem like it there, but they're getting kind of less and less negative, if you will. They're getting closer to 0. And then as you allow the x values to become less and less negative, as they head towards 0, as the x values approach 0, the y values head towards negative infinity. It's that same pattern, both sides. Now, the one value we left out here was 0 itself. If we put 0 itself in there, that spreadsheet's going to tell us error, divide by 0, because when you divide 1 divided by 0, the result is undefined. Now, this pattern here, you can kind of make some sense of why it's undefined. You've probably always been told, oh, you're not allowed to divide by 0, you're just not. But this kind of makes sense of why it is. If you look at both sides here, the patterns don't agree. The two sides don't agree. As you come from this side, the number's getting bigger and bigger, and you think it should be positive infinity. If you kept this going here, this is going to head higher and higher and higher, and you'd think that box should be positive infinity. Whereas if you come from the other side here, it looks like as you get closer and closer to 0 from that side, it's heading towards negative infinity. So since those two sides don't agree, that result is undefined. Now we're going to look right now at what this pattern in table of values, how it's reflected in the graph of y equals 1 over x. All right, to look at this graph here, let's put the function in first, y equals 1 over x. Let's change it so we can see it a little bit better here first. And we're going to put a point on this curve so we can kind of trace the values and relate it to our table that we just made. So let's do that. Let's put a point right there to start. And let's make it so we can see the coordinates here. There we go. So as we move this point now, we're going to trace out some values here. Now we had our 4 sections to our table there. We had the values as we made x larger and larger. Now we're not going to be able to see the values that I put in the table because I put 1 and then 10 and 100 and 1,000. Now we're just going to look at these values, but you can see what's happening already because as you make x bigger and bigger here, the y values are going to get smaller and smaller. As you go to the right here, this curve is going to get lower and lower. It's going to approach this axis here. It's going to behave asymptotically. This x-axis is going to be an asymptote for this graph because the values get closer and closer. The same thing happens on the other side with the negatives, right? As you make x more and more negative here, as you make them go farther to the left, that curve is going to approach that axis. So that horizontal line there, that line y equals 0, the x-axis, is an asymptote for this graph. This graph behaves asymptotically as you go to the left and the right. All right? So that's that horizontal asymptote. Now there's also a vertical asymptote that comes from that pattern that happens as we go from 1 and you get closer and closer to 0. So to look here, I'm going to spread this out a little bit here so that we can see it. And then I'm going to change the scale a little bit because otherwise we won't be able to see the axes of what's happening there. Maybe even a bit more here. All right, so we've changed the scale's not the same both ways now, right? But that's still that 0.11. So if we go from there now and we start getting closer to 0 from this right side, think about what happens with the y values. The y values are going to start getting larger and larger the way we saw. Now we're not going to be able to make them as large as what we saw on the table, but you get the same idea here. These are just going to head higher and higher and higher as you get close to 0 from this side. So you can say that this is headed up for infinity. You can say that the y values get larger and larger as x approaches 0. And you can say on the other side here, as you make x approach 0 from the negative side, in other words, as you make the x values less and less negative, if you will, the y values get more and more negative. They head down towards negative infinity. So those two things are in opposite directions. And that's part of the reason why this is undefined here at 0. Right? Now this software does something goofy. It actually shows infinity there when you land it right on 0 here. But of course it should say it's undefined. Alright, so that's a graph of y equals 1 over x. It has these 2 branches to it here. One in quadrant 1 up here and one down in quadrant 3. If you think about the values of the points there again, when we had this point in this quadrant, the 2 coordinates are both positive, which is why it's in quadrant 1, and then over here we had the 2 coordinates both negative. Alright, so now that we've looked at this first basic rational function, y equals 1 over x, we're going to look at a different one, and we're going to try and create the graph and the table by hand without using technology here, and put into practice some of the things we've discovered and seen here. So let's do that right now. So we're going to look at a different basic rational function here, y equals 6 over x, and do it without using technology here, work by hand. Now what we're going to do, a little trick that we're going to use here, to quickly generate the table and quickly create a graph is we're going to think about this as, instead of thinking I'm taking 6 and dividing it by some number to get another number, you can really quickly, it's easier to think about if you change this slightly to this related equation here, xy equals 6. If I times both sides by x, can't fit it in there, if I multiply both sides by x, I get xy is 6. And that allows you to think about this really easily. If you think xy equals 6, essentially what you're thinking about then is, I need pairs of numbers for xy that multiply to 6. So when I fill in my table, or even if I just think of pairs of numbers to graph, I can think of numbers that multiply to 6. For example, I could put 2 and 3 here. I could put 3 and 2 here. I could put 6 and 1 here. I could even put 12 and 0.5 if I wanted to, 12 and a half. Or I could go the other way here, make this 1 and 6, or 0.5 and 12. Now I can transfer those points onto the graph here, or I can just think of about those points as I'm creating this, right? I can just think 3, 2, put a point there, right, of my graph. I can think 2, 3, put a point there. I can go 6 and 1, put a point there, and then the corresponding point this way, 1, 6, and put something there. I can have 12 and a half is down there. I can have 1/2 and 12 is all of that. And if I want to draw this one branch of the curve, I can try and draw a nice smooth curve through the whole thing here. And then that's going to give me part of the graph of that thing. I'm going to put arrows on the end here because, as we saw before, the graph is just going to continue both of those directions, getting closer to the axes. Now I could mirror this on the other side. I could do the same thing. I could just recognize that I'm going to have -2, -3, or -3, -2, or -6, -1, or even again -12, -0.5, or the other way here, -1, -6, -0.5, -12. And I can put all those points on there really quick, which I'll do right now. And then we can try and draw a nice smooth curve through these points to create this other branch of this function. Not going to be perfect, but it's going to have to be good enough. And put some arrows on the end, again, to indicate that it keeps going and is asymptotic with the x-axis and y-axis. And of course, in my table here, I could also put in between here, as I got closer to 0, I should put 0 in there from either side, and this is undefined, right? Because right here, there's no value that occurs at 0, right? The two pieces of the curve are not connected to each other, and there's no value at 0 there. All right? If we had to identify the domain and the range, that's going to be our key there. The domain of this thing is, it's all possible real numbers. Even though I was just picking numbers that were easy to work with, it's all possible real numbers. So all possible real numbers such that x is not equal to 0, right? 0 is not part of the domain. It's not a permissible value there. And if we want to do the range of this thing, it's the same thinking here. The y values, you can get every possible y value other than 0, because again here, as this curve goes down here, it's going to get closer and closer to 0 but not reach it. So it's going to cover every value, every positive value. And then this curve is going to, this branch of the curve is going to approach 0 from that side. It's going to cover every possible negative y value, but it doesn't actually hit 0 itself. So for the same reason here, this is going to be, the range is going to be all possible y values except 0. So we're going to say everything except 0 there. The asymptotes, those two things, the domain and the range, are exactly related to the asymptotes, because the asymptotes, the horizontal asymptote is y equals 0. That's the equation of that horizontal line. And then the equation of this vertical line is x equals 0. All right? So that's some of the information about that curve. Now we are going to talk about one other thing that we alluded to before about this, which is two new pieces of information, or two new terms if you want. Not that they're really terms, but we're going to talk about the behavior of that curve near its non-permissible value. In other words, we're going to talk about what happens as you get close to 0 here on the x-axis. And we're going to talk about something called the end behavior in a second. So let's look first at behavior near its non-permissible value. In other words, near x equals 0. When you get close to, let's go back up to the graph here. As you get close to 0 from this side, the y values head up towards positive infinity. And as you approach 0 from that side, the y values get more and more negative here. They head down towards negative infinity. So a way that you can say that you combine those together is, as you're heading towards 0 from either side, the absolute value of y approaches infinity. All right, so we're going to say that over here, because we're not going to worry about whether it's positive or negative infinity. One side it's positive, one side it's negative. But we're going to just say the absolute value of y gets larger and larger. All right, so let's write that down here. I'll do some speed writing, if you will. All right, so there's our description of our behavior near the non-permissible value of 0. Now you notice I haven't said anything here about how the behavior is different on either side of 0. We're going to leave that more for a calculus course, even though we've alluded to it here. We're just going to say that as you get close to 0 in general, the absolute value of y gets very large. All right, that's the behavior near that non-permissible value that I've written in red there. Now we're going to look at what's called the end behavior as well. This term down here, end behavior. End behavior is what happens as you go out to the right indefinitely and out to the left indefinitely. You could talk about the right end behavior and the left end behavior. As I go out to the right this way, as the x values get larger and larger, the y values are heading for this axis here. They're getting closer to that axis. They're approaching 0. And the same thing goes the other way. As it goes kind of indefinitely to the left, those y values approach 0. So we're going to write the statement down here that all right, so our end behavior here is that as absolute value of x gets very large, either way you go, right? That's why we're using that absolute value. So we don't have to worry about saying the right and the left. As the absolute value of x gets very large, the y value approaches 0. The graph, either way, gets closer and closer to 0. This has to do with that vertical asymptote, the behavior near the non-permissible value. And this has to do with the horizontal asymptote. What happens as you go out to the right and the left? In other words, the end behavior. All right, one last thing we're going to do here is related. We're going to look at a second example here, but this one we have the graph, and we're going to quickly try and see if we can come up with the equation for that. So again, you can use that idea of looking at some key points here and looking at pairs of numbers. You first of all notice that since the vertical asymptote appears to be at x equals 0, and the horizontal asymptote appears to be at y equals 0, the equation of this thing is going to be y equals a over x. And we just need that a value. You can get the a value by doing one of two things. You can look at a pattern in points that you recognize here, 1, 4, 2, 2, 4, 1, and then on the negative side as well, negative 4, negative 1, negative 2, negative 2, negative 1, negative 4. Those are all numbers that multiply to 4. Or in other words, you have x, y equals 4. So then that would lead you to believe that that equation is y equals 4 over x. All right. The second thing you could do, if you didn't recognize that, is you could take one single point, say 4, 1, and substitute it in and then see what a value you get here. All right. So if we substituted our point in here, 4 for that and 1 for that, we'd have a over 4 equals 1, or in other words, write it over here, a equals 4. So we'd find our a value that way. Either way you do it, you come up with the fact that that equation is y equals 4 over x. All right, another basic rational function. So that's a lot of information to digest there about working with rational functions. Now, just before we wrap things up here, I think it'd be wise to summarize some of the important concepts we've seen. Now, although we looked at basic rational functions, the first thing we looked at is rational functions in general and how they are the ratio of two polynomials. We're going to look more at more complex rational functions later on, but for now we looked at basic. We found that basic rational functions have that form y equals a over x, some constant over x. We looked at how they show asymptotic behavior, both horizontally and vertically along the axes. We looked at how the domain and the range were essentially x cannot be 0 and y cannot be 0. They cover all real numbers except for 0. We looked at how the equations of those asymptotes were x equals 0 and y equals 0, where they showed that behavior. X equals 0 was a non-permissible value. And we looked at the behavior near that non-permissible value, and we described it as x approaches 0, absolute value of y gets very large. And we also looked at the end behavior, and we described that as the absolute value of x gets very large, the y value approaches 0. And then lastly here, that the function y equals a over x being equivalent to xy equals a, and that was useful in quickly creating graphs or identifying graphs. All right, so lots of information there. Take some time to process it and put it into practice. That's it for basic rational functions.